Visual Basic will say, can't do that. Yep, I'll answer his question and then yours. Yep.
And that's because of the size of the bit you're using, correct?
Well, in this case, I'm using a very kind of, I shrunk the size of an integer down to 8 bits, just so that we can deal with the numbers more easily. When we're dealing with 32-bit numbers, we're dealing with approximately positive 2 billion something and negative 2 billion something. But nonetheless, the same principle applies. It's just that your wheel is a whole lot bigger, but nonetheless, it is still a wheel and it's still a circle. Yep, go ahead.
Never mind.
Okay. So that's why this code is kind of tricky, because we will say that this is an infinite loop from the theoretical perspective. In this class, that's all you need to worry about. But from a practical standpoint, the loop does exit, okay? Because we are running out of bits to represent the value that we want to represent. Yep.
Is there ever time you want it to do this, where if you wanted to go back and sort of start over at the most positive and the most negative?
Very rarely, but there are times where you want it to quote unquote wrap around. Yeah, this is called wrapping around, and sometimes you want to wrap around with even smaller numbers like 16. So we go from 0 to 15, and then after 15, we want to go back to 0. In this class, we'll never encounter algorithms like that, but there are algorithms and practical uses of that wrapping around mechanism. Yep.
So 64-bit hardware would be even bigger.
Yeah, 64-bit hardware means we can. The most positive number will be 2 to the power of 63 minus 1, and then the most negative value will be negative 2 to the power of 63 itself. So that's how you define the range. That's how you find the range of values on the most positive side and the most negative side.
I've never heard that before put that way, that the wheel, that's a good explanation.
Yeah, the wheel is one way to visualize the whole thing. When you increase, you're turning it this way. When you decrease, you're turning it the other way. Yep.
What's the necessity for having the ability to get to such a large number?
Well, that was the question when people asked when we moved from 16-bit to 32-bit.
Well, I mean, it's 9.2 times 10 to the 18th. Like, there's no
our deficit would
practicality
get there in
ever
no
for
time.
that.
When it has to do with precision as well. So sometimes it's not just the integer that we are representing, but also the precision. Yep, go ahead.
Does hex 10 fit into that then?
Extended
Like hex 10?
hex 10,
No. The hex 10.
hexadecimal numbers.
Right.
Okay, that means base 16. Yep, base 16 is a really good base too. I like base 2. I like base 16. I just don't like decimal much.
What's base 16 used for?
Base 16 is useful because, what is the downside of binary numbers? Now, binary numbers have a lot of nice things, okay? How do I learn how to do addition in binary? This is stuff that I talk about in cisp300, but I think, an early exposure to this stuff can only be useful. I don't think anyone would find it very useless. Okay, so addition. How do we do addition? 1 plus 0 is?
2.
No. 1 plus 0 is always 1 in any base, right? 0 plus 1 is 1. 0 plus 0 is 0. Okay, the only one that is special in base 2 is 1 plus 1. 1 plus 1 is 0 with a carry. Kind of like 5 plus 5 in base 10 is 0 with a carry. That's the only special one in base 2. Am I doing okay so far? What about multiplication? What is 1 times 0 in any base?
0,
0 times 1?
0.
1 times 1?
1.
0 times 0?
0.
0. That's the entire multiplication table in base 2. Okay, so let's just say that we go back to an elementary school. I think this is like 3rd grade, 2nd grade or so when they learn multiplication. So instead of telling the kids and say, look at this huge multiplication table that you have to memorize, instead, this is the multiplication table you have to memorize. You think kids will like it? I would like it, right? How about addition? This is easy, right? So this means, when we want to carry on calculations, arithmetics in binary, it is far easier than base 10. It really is. What about division? It's much easier too. Let me show you an example of division in base 10 versus division in base 2. I want to make this really quick. So let's say we have 23 down here, and then up there. It's kind of hard to draw that picture using only text. Okay, this is division. So let's say we have, I don't know, 7, 8. Okay, that's my dividend. Okay, so how do you know we should put a 3 here? Because 78 has 3 23s, and then 4 23s will be too many, right? But how do you know that? Because you, in your mind, did the calculation. 78 divided by 23 is 3 with some kind of remainder. You did it all in your mind. But is that multi-digit division easy on your mind? What if the divisor, which is 23 in this case, what if this thing has 4 digits? How quickly can you do the calculation in your mind? Probably not very fast, and that's when you pull out your calculator, right? Okay, but in binary, it's very easy. So let me just give you an example of how to do this whole thing in binary. Okay, let's say this is my divisor. Okay, that's my actual number. All right, so there's 0 of that stuff in 1, 0, 0, 1, 0, 1. Okay, this is the only one that I can potentially have a 1. Is there a 0 or 1? I'm comparing this portion of the number with this portion of the number. Is there a 0 or 1? 0. How do you know? Did you go through division in your mind? Or did you just go through comparison in your mind? It's just comparison. Can you do comparison in binary? Is it any harder than base 10? It's easier, right? So I put a 0 here, and then I put a 1 here. Now I just want to finish one step, okay? So this is a 0, this is a 1, 0, 1, 1, 0, 1. Now I have to do subtraction in binary. Subtraction in binary is actually easier than people think. 0 minus 1 is a 1 with a borrow. And that borrow will go here, so this becomes a 0. And once again, 0 minus 1 is a 1 with a borrow. This one is a 0 already, and 0 minus 1 is a 1 with a borrow. So the borrow goes here. 0 minus 1 is 1 with a borrow. That borrow goes here. 0 minus 1 is 1 with a borrow. And then 1 minus 1 from the previous borrow is a 0. And then 1 minus 0 is a 1, but since I have a borrow from the other one, so this becomes a 0. It's actually easier than base 10. Okay? So binary numbers has all these advantages, okay? Easy to remember, because all the multiplication table, division table, and whatnot, not division, multiplication table, addition, and stuff like that only have 4 items. 2 by 2 matrix. Okay? Very easy to deal with. What is the one downside of binary numbers?
Number of digits.
Exactly. It takes a lot more digits to represent something. What is our current national deficit?
14 trillion.
16 trillion. 16.9 trillion.
Okay, 16.9 trillion. Okay, let's think about it. Okay, so let's find out how many digits it will take in base 2 to represent 16.9 trillion. Okay. Okay. Now I don't need the exact number. I just need you guys to know how to do it really quickly. Okay. The quick trick here is to remember 1,000 in base 10 is approximately 1024, which is 2 to the power of 10. Now that's a very useful approximation because now you can say, what is a trillion? How many zeros do we have in base 10? 12 zeros, okay? So that means a trillion is 1,000 to the power of 4, right? Which is approximately approximately 1024 to the power of 4. 1024 is 2 to the power of 10 to the power of 4, the whole thing. So this part here is about 2 to the power of 40. Okay? Now we only have the 16 or the 16.9 left. 16.9 is more than 16, and it's less than 32. So we'll just say it's the 32. 32 is 2 to the power of 5. So when you combine the two, 16.9 trillion in base 10 can be represented in 2 to the power 45 bits. 40 bits to account for the trillion, and 5 bits to account for the 16.9. Okay? We got 45 digits instead of the other one would be, well, we've got 12 and then we have 14. Okay, the other one only has 14 digits. Okay, so the number of digits is really off. It's off by maybe 3 point something. In other words, if you need X number of decimal digits, if you multiply that by 3 point something, which is the log of 10 divided by the log of 2, then you need that many bits, binary digits, to represent the same value, which is kind of a hassle, right? I mean, if you just, okay, go back home and look at your balance, okay, your bank balance. And for some people, maybe the credit card balance. And then you think, okay, with all these decimal digits, how many binary digits do I need to represent the same value? It's a lot, okay? And it's a mouthful to say things in binary because it's all zeros and ones. It's hard. It's very easy for someone to miss one digit, right? Because it's 1 1 1 0 1 0 0 0 1 1 0 1. It's easy to miss. So that's why we don't like binary numbers when it comes to actually writing it down, or just telling another person how much we are talking about. And that's why we have base 16, hexadecimal number. Hexa means 6, deci means 10. So when they combine, they become 16. Okay, 6 and 10. All right. So let's come up with a binary bit pattern here, and we'll try to figure out how to represent it or speak it out as hexadecimal. Okay. All right. That's this is too repetitive. Okay, let's call it good. Okay. So the first thing you want to do is to chop it into chunks of 4. And I always start from the least significant digit, which is on the right-hand side. All right, wow, that's even. Cool. And not only that, it has exactly 32 bits, which is really freaky. Okay, then you look up a table, okay? For those of you who are not familiar with hexadecimal numbers yet, you can just look up a table that has exactly 16 items. Okay, the 16 items will go from 0, 0, 0, 0 on the binary side to 1, 1, 1, 1 on the binary side. On the hexadecimal side, it will go from 0 to 9, and then A, B, C, D, E, F, to represent 10, 11, 12, all the way up to 15. Okay, but since I have that table already memorized, this is A, 2, this is E, A, 6, F, 1, 7. So in hexadecimal, the same value can be represented as A2EA6F17.